Hello everyone, Assalamualaikum and a very good day to all of you. So I just want to share with you how do we can actually find the H equations or the value of H that actually penetrate from the current source to the certain point of interest. So if you can see from this diagram, this is our filamentary current that ranging from A to B, and also this is your point of interest located at any point around the line current, they say at R, V and Z. And bear in mind that guys, this is a constant value. It means that the point that doesn't change, it's remain there. Alright, so the R is measured from the line current to the point of interest that perpendicular or normal, and then this is your Z, the height of the point of interest. Alright, so from Biot-Savart law, you can see from these equations, dH is equal to I dl vector plus unit vector of R over 4 pi R squared, and this also can be transformed to other form as shown here, I dl vector plus R vector over 4 pi R cubed. And then this R, guys, is actually a vector that joining from the current element to the point of interest. So the first step, now you have to choose or select any point within the line current to be our sample current or our current element. Let's say this is my positions of current element. I choose from here. Okay, and then let's join them between the current element to the point of interest. So that's going to be our R vector. Again, the R vector is vector that joining from the current element to the point of interest. So let's say this current element located at Z prime. It means that the positions of current element could be anywhere along the line current from A to B. So just put anywhere and label different forms as Z prime, because here we have already Z. So use other form of labeling. So here put Z prime to make it different with the positions of point of interest. So that's our positions of current element. It must be anywhere within the line current. Okay, so from this diagram we can get the R vector as shown here. The R vector is equal to the R component, this side, plus this side, minus Z prime minus Z component. Okay, so this is a vector of R. Is composed of two main components in R and also in Z. The R positive because coming out radially outwards, and then the Z is downwards, got negative there. Alright, so now this is your current element. It's given as here I dl vector. We know that, guys, this line current or this current lies on Z axis, so by right we can convert this dl vector to the more specific value, becoming I dz component. And bear in mind, guys, this current element referring to this sample or this current element, so we have here put become dz prime, then make it valid. Alright, because this current element refers to the sample or the current element, so this here must become dz prime following this label. So, okay, done. So let's put in all the value IDL to be here, the R to be here. So what's going to happen here? The I dz prime Z component plus the vector R component minus z prime minus z component over 4 pi r squared z component minus z squared 3 over 2. Okay, so now if you can see that now we have a cross product between the z and r, and also between the z and z. Alright, we know that this product output will become 0. Z dot z will have 0 output for sure. And now how do we find the cross product between z and r? So let's do this simple analysis between cross product. Let's say we have here the z, here we have the r and the phi. So when the r cross phi, we are going to have z. When the phi cross z, we are going to have the r. Same thing goes here, if you do z cross r, we are going to have the phi component. So this case, we have z cross r, so that should be our output for this cross product. So here you can just put here phi component. Alright, so let's split the equation, take out all the constant out from the integral part. So now I just want to focus on the h. So we have this r actually our constant, constant, and constants. So we have here the output is phi just now, then here I r over 4 pi, and then now we have to integrate the dz prime shown here, integrations dz prime r squared z prime minus z squared 3 over 2. Alright, because we lost already this term, we don't have any more, becomes 0. So now we have to integrate this part. So referring to the table given in Sadiku book, you can simply convert this integrations process becoming to this form phi ir 4 pi, and then here we have here z prime minus z over r squared plus z prime minus z squared 1 over 2, and the limit should be from a to b. This is the limit for the line current. So here should be your limit from a to b. Same thing goes to up here from a to b. So let's substitute the limit within the equations. You can see from here the phi component ir over 4 pi, and put the b inside the z prime, because z prime is your main parameter, or your parameter of interest of the integration. So the z here is constant, the r here also is constant, so nothing changed. Just plug in the a and b value into the z component or z parameter. So now we have here b minus z over, okay guys, before that we just delete this r, because we have here 1r, so here you can have only left 1r, right? So the r here got r squared, so here we lost the r, and here we have the r squared plus b minus z squared 1 over 2, and then a minus here a minus z over r squared a minus z squared 1 over 2. So that's our substitutions A and B inside the equations. So how do we find these conversions or this term over here? So we can simply find the term just taking the triangle from the line current to the point of interest. So let me draw for you. Okay, so if you can see from the diagram here, I want to show you how do we find the value of the relationship between the line and also to the point of interest. So let's say that's your triangle showing our line current just now. Okay, and then this is your point of interest. So let's join them, and this is our radius, which is normal or perpendicular from line current to the point of interest. And this is our joining line from lower limit, which is A, to the P. It's your A, and then this is B, your high limit, and this is your line joining from high limit to the P as well. Okay, and we know also this actually become your Z, right? As shown before. So Z is your height of the point of interest. So let's define this angle. You see properly the directions that I draw here. From normal line to this AP line is going to be our alpha 1. Again, from normal line to the BP line become alpha 2. Okay, we know that this distance become B minus Z, the difference between these 2 points, and also difference between these 2 points I have here Z minus A. And also we can find this length using theorem Pythagoras as shown here, R squared B minus Z squared square root. And also from this length you can have using theorem Pythagoras as well. So the R squared plus Z minus A squared square root. Alright guys, if you see closely to these equations, we can notice that this term actually refers to this term shows us sine alpha 2, isn't it? Because sine alpha 2 actually B minus Z as shown here over this line as shown down there. So, and also from this side you can see from sine alpha 2 or sine alpha 2, right? This one, sine alpha 2 means sine alpha 1, which is Z minus A up there over this line. So we can simply replace or substitute the conversion for this particular equations, whereby this term is going to be our sine alpha 1 and plus this term to be our sine alpha 1. So finally we're going to have our equations for the infinite line current. Phi I 4 pi r sine alpha 2 plus sine alpha 1, and the unit must be in ampere per meter. Alright, so guys, this is how we solve these problems. So this technique can be applied to find any other structure of line with either it's finite or infinite, or even in other structure like a circular. I will show you afterwards. So now I would like to draw your attention. What happens if, let's say, we are going to have a very long line current, for this case? So what's going to be happen, or what's have to change to the equation down here? So if you see closely to this diagram, if we extend the line current to be very long downwards and very long upwards along the z-axis, you will see that this alpha 1 will reaching to 90 degree approximately, show you down here. You see, very long. So the alpha 1 will reach 90 degrees approximately. And also from this case, if you increase to very long line current, the alpha will increase until approximately 90 degree. So you can see that from this equation, you know that when the line current extends to infinity long, so you see that the alpha 1 and alpha 2 will reach 90 degree approximately. So we can simply put the value inside the equation just now. Gonna have here the hash phi I 4 pi r. Now here is sine 90 degree plus sine 90 degree. This one got 1, this one 1, so plus 2, and then over 4. You have finally your equation phi I 2 pi r ampere per meter. So that's equation for the infinitely long line current. Alright guys, so I think that's all for today, for this time. Okay, thank you for your attention. I hope you can try yourself and check it out, is it true or not with your solutions with me. Okay, thank you.